Okay, chapter 21 is preparing a buffer. As you know, we took notes on what a buffer is, and a buffer is something that has the ability to neutralize the addition of an acid or a base when added to it, and the pH does not change very much. Okay, the most important part of buffer problems is almost always there is a weak, why does it keep doing that? Weak substance with some sort of salt with the weak substance. Now, whether the salt is thrown in there or the salt comes from a neutralization process, you need a weak acid or a weak base with the salt that has part of the weak acid or weak base in it, also known as the conjugate. Okay, so identify the major species. We've got ammonia, weak base. Okay, and then we've got ammonium chloride. +1 -1, that's ionic, so it's our salt. All right. So what does our weak base do? Our weak base goes like this: ammonia plus water. We write our weak base in equilibrium because it's weak with its ions. Bases accept hydrogen ions. The water loses the hydrogen ion to make hydroxide, and that is our weak base equation. Okay. Notice this isn't necessarily a chemical reaction. What I'm doing is I'm taking ammonia and I'm also taking a salt. Now, if you notice, there is part of my salt that looks a lot like my conjugate to my base. That's what this is. Okay. In order to form a buffer solution, you need a weak substance and its conjugate present in good amounts and significant amounts. A weak base alone does not ionize very much. So the weak base is mostly all of this and very little of the ammonium ion and the hydroxide ion. However, if you introduce to the system a salt that we assume 100% ionizes, so let's write our salt. Ammonium chloride. And unless this is a KSP problem, which it's not, I don't see KSP anywhere, we're going to assume our salt is soluble and 100% ionizes. And now what is great is I have ammonium coming from the fact that I have salt in there. Okay, so what we're going to do is there are two ways to go about this. You can set up a KB expression for your weak base, okay, or we can set up Henderson-Hasselbalch. So let's look at Henderson-Hasselbalch. Now, we haven't done this with a base yet. So the Henderson-Hasselbalch equation is for a buffer, and we know this is a buffer problem. So I'm rewriting it out. Remember, the weak always goes on the bottom and the conjugate always goes up top, okay? This would be great for a buffer if there was an acid, but this is a base. So I'm going to rewrite Henderson-Hasselbalch, and this is not on your equation sheet. So if you are capable to reinterpret, instead of pH, I'm going to do POH. Remember, OH is base. And then instead of pKa, I'm going to do pKb. And then I'm going to do the log, and then if the weak acid is what's on the bottom, then the weak base, which is B, is on the bottom. And a conjugate of a base, what do bases do? They accept hydrogen ions, so BH plus is its conjugate. This is a generic Henderson-Hasselbalch equation for a base. So I want to know the moles of ammonium chloride needed, okay? And I know what the pH of the system is. It's 9. This should make sense. There's a base in there, okay? So it's a pH of 9. So what is the POH? Well, it's 14 minus 9, so that's 5. Is that right? 5.00 equals pKb. What does P mean? P means opposite the log of Kb, and the Kb is given as 1.75 times 10 to the negative fifth plus the log. The concentration of base being used, ammonia, is 0.1 molar. Okay, and then this is ammonium concentration. That's its conjugate, right? Ammonia and its conjugate. So I can solve for the concentration of ammonia, and then once I know concentration, I can use molarity and volume to get us moles. So plug all this in your calculator. I'm going to let you do that. When you solve, let me see what I've got here. I get the ammonium concentration after all the rearranging to be 0.175 molar, okay? Which would be great for concentration, but I specifically asked you moles. Well, molarity times volume is moles, and the volume of our container is 2.0 liters. So the number of moles is 0.35 moles of ammonium. And you go, but they asked for ammonium chloride. Well, for every ammonium you have, there is one ammonium chloride. So that is also 0.35 moles of ammonium chloride. Now, they could make you take this one step further and you would be asked to determine it in mass, so you just would turn moles into grams using molar mass of ammonium chloride. But again, this is the Henderson-Hasselbalch equation for a buffer. We know it's a buffer problem because it says buffer right there. Okay, so you can use the buffer equation, plug and chug what we know in. We solve for molarity of the conjugate, and then turn molarity into moles per them asking for moles as opposed to molarity. Again, in order to have an effective buffer system, you must have a weak substance, weak acid or weak base, with its conjugate present. So a weak base alone is not a buffer. Oh, I was almost done. A weak acid alone is not a buffer. There must be some source of its conjugate present in order to be an effective buffer. And in this instance, ammonium chloride, the salt, is what gave us its conjugate that allowed this to be a buffer system.